Good morning, everyone. Today I'm going to be talking about ways of using some insights from formal semantics to help us build better models for grounded language learning. So we're going to be focusing mostly today on the problem of question answering. So here's an example of the kinds of problems we're interested in. We have a question that's been generated by some kind of human speaker. We have some kind of representation of the current state of the world. And our goal is to build some kind of system that can take these two things as input and generate the answer to this question as output. And the way state-of-the-art approaches to this question answering problem, and a lot of its forms work right now, is by transforming text into some kind of logical representation of meaning, and then interpreting that representation of meaning according to the model provided by this database. And this line of work here, I think, is really one of the triumphs of linguistic formalism in natural language processing, right? These approaches have benefited from years of study on how to represent things like events and quantification. They're really data efficient, they're interpretable, and in many cases still better than the fanciest kind of end-to-end neural thing that we know how to build right now. The problem here is that the world doesn't actually look like a database most of the time. And these kinds of logical approaches really break down as soon as we're confronted with any sort of world representation that isn't already written in the target formalism. And that's basically everything that we actually want to do, right? So we're mostly going to be focusing on answering questions about images today, but think also of unstructured text documents and video and audio and really any kind of free-form representation of the state of the world. And in these more unstructured settings, most of the approaches that are out there right now do work by writing down some kind of big neural net that's going to slurp up your question and slurp up your representation of world state and spit out the answer on the other side. These approaches actually work remarkably well for when you have enough data and when you have simple enough questions, but they struggle to deal with small data sets and they struggle to deal with generalization in a way that we'll see in a little bit. So our goal today is going to be to get the best of both worlds, to build some kind of model that enjoys some of the statistical efficiency, maybe even some of the interpretability of these approaches backed by logical representations of meaning, but at the same time to build something that we can actually apply to unstructured world representations like images. I think the abstract in the program today also mentions something about distilling interpretable structure from deep models. There may or may not be time for this, but we'll come back to it at the end. For now, let's just talk about this question answering stuff. So what's it going to take to actually build a model that achieves these goals that we've laid out so far? And in the crudest possible terms, if we want to build a system that's going to understand language in this way, we need to understand what words mean, and we need to understand how to put words together. And toward this first problem of figuring out what words mean, the real lesson of the last 5 years has been that neural networks are shockingly good at this, right? If I want to be able to recognize something like a circle or something more complicated like a soccer match, starting even from something like an image, these are really the right tools for the job. On the second problem of figuring out how to put words together, I think we've seen a little less evidence that these kinds of neural models are able to generalize compositionally in meaningful ways. That, like Sharon was saying yesterday, a lot of this is really just about learning similarity and not necessarily about sort of conventional notions of linguistic productivity. But this is exactly what these kinds of formal approaches, and especially the formal approaches backed by explicit grammars and explicit lexicons, are really good at. So in some sense, all we're trying to do today is to get the best of both worlds here, to sort of be able to learn these kinds of rich expressive primitives that we know we're really good at getting from neural networks, while hanging on to the kind of compositional power that we get from these logical approaches. And we're going to be doing this today with a class of models that we call neural module networks. At a very high level, these neural module networks work in the following way. The result of learning is going to be some kind of collection, think of it as a lexicon, of little neural network fragments that we call modules. And if I see a new question, like is there a red shape above a circle here, I'm going to parse that question, and I'm going to use the parse to construct on the fly some kind of question-specific neural network that's laid out according to the structure of that analysis. And then I'm going to take this question-specific neural network that I've built up, I'm going to apply it to some kind of representation of our world state, and we're going to get our answer out the other side. Before going into the details of how this approach works, I want to spend a little while motivating some of the representational decisions here and in general some of the kinds of things that a grounded question answering system like this needs to be able to do. And as we suggested before, one of the really basic things we need to be able to do is to figure out what a word like red means here. And what does red mean? Well, again, the answer that we get from model theoretic accounts of semantics is that we want to think of red as some kind of function that takes us from our world state to some representation of the set of things in the world that are red, right? And similarly, think of circle as some kind of function that's going to pick out a representation of the set of circles. And more complicated things like above as functions that can transform one of these initial sets into a representation of the set of things that are above those entities. And more generally, we can think of every utterance as being associated with some kind of tree-shaped or maybe graph-shaped computation that's going to tell us how to evaluate the truth conditions of a sentence or how to generate answers to questions with respect to a state of the world. And this computation is going to be built up of a collection of little logical and functional primitives. And in these sort of purely formal approaches, we think of these primitive functions typically as communicating with each other in some kind of language of sets. Parenthetically, the way we've written this computation down is using a particular variable-free formalism. If you're more used to seeing something like the lambda calculus, these are all kind of syntactically equivalent. We can always transform lambda expressions into something that looks like this. But to back up, past work has typically assumed that with these primitives, the implementation is known. So the only learning problem we have here in building a question answering system is figuring out how to put these structures together. And again, this works well as long as you actually sort of know everything about the structure of the world, and everything that you need to know about the set of relevant primitives is given to you by something like a database schema. It falls apart as soon as there's non-trivial structure that you have to put inside the functions themselves, or equivalently, that structure doesn't exist in your world representation. Today we want to be able to learn both things at the same time. And our entry point into this is going to be the following trick, essentially. That rather than having these little computational primitives that we're working with communicate in a language of sets the way we have in formal approaches, we're just going to relax that and let them send real valued vectors instead. We'll talk about the semantics of these vectors in a little bit, but fundamentally and at a high level, we now have a view of the world that looks like this. This utterance-specific computation graph that formal semantics tells us to build to interpret a particular utterance is something that's going to take a feature representation of the world as input. It's going to pass it through a bunch of vector-valued intermediate states. It's going to generate some kind of distribution over answers at the end. And what is a function, from input features through a bunch of vectors via nonlinear transformations to outputs? That's what a neural network is, right? So as soon as we've relaxed from this kind of classical set-valued semantics to this real-valued thing that we're doing here, we're essentially committed to a view of the world in which logical forms are implemented as neural networks. So as we suggested at the beginning of the talk, think of each of these things that used to be some kind of formal primitive as now being associated with some kind of shallow neural module. And where we're accustomed to building up logical forms, we're now going to build up networks of these modules. And we can view these things, again, either as sort of monolithic neural networks that we can train in the way that we're accustomed to training them, or as composed objects that we can manipulate in the way that we're accustomed to manipulating the corresponding logical objects. So in what follows, I'm first going to start by talking about how we actually implement these little modules, and then a little bit about how we actually learn them in the context of larger structures. So the first question that we have to answer here is what actually goes on inside one of these things. Well, they implement functions. So like any function, the first thing that we need to know, or the first thing that we need to do is to start by specifying what kinds of types they're going to act on. And here, again, we're going to use a type system that really looks very familiar from formal semantics, that basically acts on some sort of soft notion of a set of entities and some soft notion of a label. So I can have functions like relations that take me from collections of entities to other collections of entities. I can have simple predicates that generate initial sets of entities. I can have something that looks like an accessor function that extracts some kind of property from one of these sets. And we can actually implement some, but not all, quantifiers in the same way. And so these are basically the kinds of type signatures that we're dealing with when we implement these modules. And the only other thing that we need to know is what function actually gets implemented by one of these things. So we're going to associate also with every module some kind of lexical parameter that specifies the precise behavior that it actually implements. And just as a kind of reminder of what the stakes are here, right, these things need to be designed in such a way that they can work not just on grids of toy-colored shapes, but also messy things like real images. And maybe we even want to be able to design them in such a way that they're sort of backwards compatible with these database worlds that we've been used to working with before. Obviously not time to go into the details of how we implement all of these things, but for a little flavor, let's just look at predication. So here's a module that's going to look for circles. And one way of implementing this is to start by assuming that our input representation of the world consists of some kind of collection of atomic things at some level of granularity, each of which is associated with some kind of feature vector. In these toy shapes worlds that we're describing, we've been drawing these little atomic things as exactly corresponding to complete shapes. In general, that's not going to be true. These might be kind of arbitrary patches of images picked out by some kind of convnet. Just think of them as little local feature bundles. And when we're looking for circles, we're going to take each of these atomic feature bundles, we're going to concatenate it together with a parameter vector associated with the lexical item circle. We're going to pass this whole thing through a multi-layer perceptron, and the output of this multi-layer perceptron is going to be some kind of scalar judgment about how likely it is that the particular atom that we're looking at now is or is part of or contains a circle. And we're going to sweep this operation over all the atoms in the world, and what we get out at the end of this process is some kind of heat map that tells us where all the circles are. I want to note here that this is certainly not the only way of implementing this kind of operation. When I was putting these slides together yesterday, it occurred to me that if you think of these input feature bundles as corresponding to tensor product representations, it would be very natural to implement this using a kind of unbind and test operation like Paul was talking about yesterday. So yeah, I think the high-level details of this framework don't really depend on the individual module implementations, but this is one that's worked well for us in the past. So now let's talk about learning. The great thing about this framework is that learning is really easy. So suppose, to start with, that we have a data set consisting of just question, image, answer, triples. And let's suppose for the moment that we already have some way of transforming the questions expressed as natural language into these network layouts. Then we can think of the whole learning problem that we're faced with here as basically a bunch of teeny little supervised learning problems for a bunch of different neural networks, one per question, where our goal is sort of locally to maximize the probability that each of these little networks gets the right output for the particular input that we've shown it. And the only thing that's going to impose any structure on this collection of teeny little learning problems is the fact that where one of these modules shows up in multiple different places, we're going to tie the associated parameters together. And what we actually have at training time is something that looks like this, or something even more complicated than this. It's a mess. Fortunately, nowadays it's pretty easy to implement these kinds of things in modern deep learning frameworks, thanks in part to some people who are in the room right now. And once we've fixed our network layouts, and once we've set up this kind of structured parameter tying, the only learning problem that we have is normal maximum likelihood estimation subject to the constraints provided by this parameter tying scheme. And we can just press go on our optimizer and our answer will come out. Despite the fact that learning is simple here, it has a couple of features that I think are worth dwelling on for a minute. The most important of which is that the specialization of these modules to the individual behaviors that they take on is entirely driven by the structure of this parameter tying scheme, right? There was no point in this whole process where we actually said, okay, hey, you above module, here is a supervised example of the transformation that you're supposed to be applying. Or hey, you circle, like, here's a collection of all of the circles here's a representation of all the circles that are in the images. All we have are questions, images, and answers, and the specialization has to just fall out of that. We're going to see in a minute that these things do kind of acquire disentangled behaviors in the way that you would expect them to, but that's just because basically they have to in order to play nicely in all of the different contexts where they occur. The second noteworthy feature here is that one of the things that makes normal semantic parsing hard is that there's this kind of hard embedded combinatorial optimization problem where I need to figure out how to line up all of my lexical items green with my semantic primitive tokens green prime. In this view of the world, there is no such thing as green prime. There's just words and the sort of raw features of observations that they pick out. And so the problem of learning the semantic lexicon lives entirely in the problem of learning the weights for these little modules. So finally, where do these layouts actually come from? And here, again, the great thing is that because these network layouts are basically isomorphic to logical forms, we can just plug any existing broad coverage semantic parsing framework into our system and consume its outputs in that way. And this has a couple of consequences. Most importantly, it means that we don't need grounded data to learn how to generalize to new syntactic structures. We can do that with existing tools that are maybe trained in different ways, and more generally we can be kind of consumers of new developments in semantic representation and semantic parsing more generally. At the same time, a lot of the tools that are out there right now are a little brittle or make distinctions that are not quite the ones that we want to make. The thing that's actually worked best for us so far is a kind of hybrid approach where we use basically the phrase structure of the question to build some kind of delexicalized template for a semantic parse. And then we use the standard neural attention mechanism to actually figure out how to assign particular pieces of the sentence to pieces of this parse. And so what we're basically telling the model is, here's some kind of high-level logical scaffolding that we think is pretty close to correct. Use it or don't use it as you see fit. And there's nothing stopping the model from sort of jamming the whole sentence into just the top of this and not using any of the structure. The exciting thing is that the scaffolding actually does get used. So let's look at some examples of this. Here's an example of a question from the recently released Clever data set. So the question we have here is, does the blue cylinder have the same material as the big block on the right side of the red metallic thing? I'm sure it's totally obvious to everyone in the room that the answer to this question is yes. I'll note right here that the data generated and also the images are all synthetic, so we're not really doing natural language processing yet, but it's useful as a first set of diagnostics. And here's what our model does on this example that we had on the previous slide. And hopefully you can see from far away that we really are doing the right thing, that the model finds a blue cylinder and it picks it out right there. It finds a red metallic thing, it picks it out on the right side, and does the appropriate spatial transformations and filtering operations. And so even though we've never seen an example of finding a red metallic thing in isolation, the model has still learned a sort of disentangled way to do that. And of course, this isn't just for fake data. So here's an example from the visual question answering data set, which has real human generated questions and photographs. And we can see again that what we're getting out here is a plausible analysis and basically an accurate representation of this spatial relationship behind. If we care about numerical evaluations, basically the takeaway is just that the system is at or near the state of the art on a bunch of data sets, including these synthetic images, including natural images. Here's a slightly different data set involving sort of truth judgments about, again, sort of complicated fake scenes. And here we're substantially better than the best thing out there. We don't just care about visual question answering. We said at the beginning of this talk that we might also want to be able to handle the kind of old school logical worlds as well. And so one of the things that I find really exciting about this framework is that we can just drop it in there basically unchanged and have a start on similar other kinds of problems. So here's one of these database-backed question answering problems we were looking at before. And with an appropriate set of these little neural modules, an appropriate representation of the database, we can here basically outperform the best logical approaches, even in domains that are purely logical in structure. The last set of experiments that I want to show here is one that I hope this group will particularly appreciate, and I think it's related a little bit to some of the poverty of the stimulus experiments that we were looking at yesterday. There are models out there right now, as we saw in the previous slides, that are a little better than this approach on natural images and a lot simpler. But if you change the training distribution at all, these approaches totally fall apart. And so what we're doing here is we have a set of experiments from one of the earlier papers, again back on the toy shapes data, and at training time, the model is only ever going to see questions that look like the ones that we have at the top, where we say things like, is there anything left of a circle? Is there anything above a circle? And only at test time are we actually going to show the model sort of more complicated questions that it's ever seen, where in this case it just means we have kind of conjunctions and it gets to be asked about multiple things at the same time. And in this setting, basically our approach doesn't suffer any kind of drop in performance, while the results for the other systems are substantially worse. And the reason is that because our semantic parser knows what to do with these new sentences, even if the actual grounded part of the system has never seen them before, we're able to sort of put together the right structure. And the key takeaway here is that basically we can use linguistic theories and linguistic structures to build models that generalize in this way, even when those linguistic theories themselves are not able to or designed to model large parts of the actual downstream tasks that we're trying to solve. More generally, what this framework gives us is a way of using linguistic structure as a scaffold, essentially, on which to hang whatever kind of free-form neural model we want. And we've seen that by doing this, we can build effective models for a couple of different language processing tasks. So that, I think, is 20 minutes, so I'll go to questions. Thanks. And credit also to all of my collaborators at Berkeley, and especially Ronghang, who is responsible for the bars being tall. All
right, we have most of 10 minutes for questions.
Yeah.
Thanks for your talk. And sorry if this is naive or I've understood you incorrectly, but you say that all of the semantic subtlety lies in the layout of the modules?
I wouldn't say all the semantic subtlety lies in the layout, right? So for example, there are kinds of things that are like super hard to model in a purely logical framework that these sort of neural blobs are pretty good at, right? Like if I want to be able to distinguish between a tall building and a tall person, trying to disentangle that at the level of this logical structure. I mean, it's something that people work on, but it's like a lot of work. Whereas we can just say, this whole string, tall person, recognize it. So yeah, I think there is lots of logical subtlety that can go on kind of below the level of logical structure in these models, but also some at the top level as well.
I guess I wonder, would there be any feasibility of looking, once you've got your set of modules and your layout, and you've got, your image of what that is, would it be possible to have your model replace a module? If it's like, I know you said there's no such thing as a degree in time, but do you see any possibility of something like that if you see like a very unlikely layout come out, or maybe an improbable?
Oh, you're just saying if the semantic parser itself is wrong, can we kind of learn to recognize bad semantic parsers? Yeah, so I didn't talk about that at all today, but in fact, one of the things that helps us get good results on a bunch of these data sets is to sort of learn to imitate an off-the-shelf semantic parser, and then do a little reinforcement learning on top of that to fine-tune the results. And in some cases, we can learn to correct either deficiencies in the semantic parser or deficiencies in like our implementation of the pieces. So you see it kind of like where we haven't given the model enough computational power to implement some primitive, it'll just like stack a bunch of little modules on top of each other until the thing is deep enough to implement what we want. But yeah, I think there's certainly room to correct inline or post hoc these analyses. Yeah.
Brendan O'Connor at UMass. So if you have, is there any way to deal with genuine syntactic ambiguity from the graph? If there's a PP attachment ambiguity or coordination ambiguity, can you get like multiple of the graphs? And
we don't right now, but it would be really easy in this framework to marginalize over those structures or max over those structures or whatever. Yeah, so I think if you believe that that's the right way of handling ambiguity, then we can instantiate that at the top level here. Yeah?
And something slightly related, like the problem of polysemy, when you're tying all your things together and you're forcing the similarity of weights, do you have any way to worry about that, or at this point you're just assuming that, or you're just dealing with things where there's not?
Yeah, so I mean, I think it is probably the case that in all these data sets, polysemy is not really an issue. At the same time, I think there's some reason to believe that we can have one module associated with one lexical item that can recognize the various distinct meanings associated with that. But again, this is something where if you have like an off-the-shelf system that can do word sense disambiguation, and you want to consume the outputs from that and give the different senses different implementations, you're able to do it in this framework. Yeah?
Could you say something about how you deal with operator variable binding?
So again, for a lot of the things that we're dealing with here, there's not actually that much variable binding that you have to do at the top level. I don't think we're doing anything new in this respect, but like if you've seen some of Percy Leon's work on dependency compositional semantics, where basically you pull all the quantifiers out to the fronts, and that's the only place you actually see variables. We can basically do that in this framework. At the same time, I think we're probably, like our ability to handle really complicated things with quantifiers and lots of variable binding is still probably pretty weak here. Yeah?
Chair, we're going to ask a question. Have you done, I love the bit where you could sort of see that it was doing something compositional. Have you done a broad scale analysis of that to look into what kinds of structures it finds and what kinds it seems to skip over, for example?
Not really. So, I think on these the 3D shapes things, it seems to be basically right. These examples are a little cherry picked, and there's some cases where it's clearly learned some disentangled representation, and it's mostly like really clean spatial stuff, and then everything else, you look at these attention maps and it pulls out the whole image, but we haven't done any kind of like large scale going through and annotating the errors. Yeah, Jason.
So this work's been about questions.
Yeah.
And I wonder about generation of statements and how that might fit into this kind of compositional theory. Yeah, so that's a great question. I think in some sense, the right thing to do here is if I have some, say I want to start with an image and I have I want to figure out how to ask some question, the answer of which is given to me
you can imagine like searching in the space of these structures until you find one such that when applied to the image, it gives you the answer out, and then you have some way of translating the structure back into natural language. We haven't really done anything like that yet, but I think that's the right way of thinking about it. Yeah.
And starting with questions actually gives you a kind of a natural topic focus structure to sentences that you might produce. So if the idea is your communicative intent is to ask a question and give somebody the answer, you can construct a question that would have you can construct the question and the answer in this format and then transform it from a question to a statement.
Right, and there's this whole, like, a bunch of people working now on these kind of neuralized, like, rational speech acts models and other sorts of pragmatic models of sentence generation. Basically, anywhere in one of those models where there's something that looks at the world state and generates behavior, you can plug in one of these things instead. And so I think, on the generation side, to the extent that this framework is pretty narrowly targeted towards interpretation instead, that's where it comes in.
One last quick question.
Could you say anything about the part of the talk that you said you would talk about at the time?
Okay, so this is actually a little bit related to the thing that Jason just asked. Let me see how quickly I can do this. Here, consider the humble encoder-decoder model, right? I have some kind of neural network that is going to look at something, generate some encoded representation of it, hand it off to another neural network that's going to do something with that representation. If you cut these things in half and you look at the final hidden state generated by the encoder, you can kind of think of this in a weird way as being analogous to a referring expression game played between two people, where the encoder is the speaker and the decoder is the listener. And so if we get people to do the same kinds of tasks that we do with encoder-decoder models, where we actually make them go through a linguistic bottleneck, we can kind of use, again, these like model theoretic accounts of semantics to say, okay, think of the logical form associated with the human utterance as generating some kind of denotation in a particular context for the sentence, and think of the decoder model as also generating a denotation for the encoded vector representation in the same context. We can then like translate encoded vectors into natural language by searching in the space of denotations until we find things that line up. And you can then basically use translation pairs that are tagged with logical forms that participate in particular structured relationships to find geometric regularities in these vector spaces. So basically you can like take a vector that the encoder has produced, apply some transformation that you learned offline that you think does negation to it, hand the negated vector off to the decoder, and you'll see that the decoder actually like generates the negation of the behavior that it would have gotten when you started out. And you can actually also use kind of side information from language to mine for these vectors that participate in structured relationships, and then actually see interesting things about the geometry. So that's the 30-second version.
And it just fit, so thank you.